Here's a rather tricky question on hydrostatics, or actually, this is more related to the idea of mass, volume, and density, which most people think it's nothing too difficult because it's something that we learn at an early age when we start learning physics, which is we learn that density is mass over volume. Now, keep in mind this works for homogeneous objects. If your object is not non-homogeneous, then it's a bit different. But even in this simple case, when density is just mass over volume, this idea can be taken to create some really tricky scenarios, which is what we're going to look at here. So let's read the question. And by the way, if you have any problems that you'd like to see on the channel, whether they're fluid mechanics related or otherwise, let me know in the comments. So we're dealing with a cylindrical vessel, which is, so the first key word to keep in mind is the fact that this is cylindrical. Okay, this is going to play a role later. Now, this is filled up with water to a height of h0 equals to 1 meter. So what we have is we have a vessel, and at the beginning it's filled up with water up to 1 meter. Right, and then we drop a large number of some pellets, some iron pellets, and they're being added to the tank until we reach this scenario here. So this is when the topmost layer of the iron pellets. So what we are actually looking at, if we zoom in a bit more, what we'll see at the end is that the layer of water is here. Let's try to make it straight. And the pellets are going to be just underneath it. So the top layer of the pellets are going to be just underneath that layer of, just underneath the free surface actually. Okay, one here and well, let's squish one more here. Yeah, so we add a certain number of them or a certain mass of them. We don't know that, but what we do know is that the density of the iron, that's what the pellets are made of, is this. We know the density of the water, which is this. And then we're given this interesting idea. The average density of the contents is 4,070 kilograms per meters cubed. Okay, now we're going to explore this in a second, but let's try to find out what we have to calculate. So the question is asking, find the height of the water level with the iron balls. Okay, so we're trying to find this. So that's the height we don't know. So we have a cylindrical vessel, and that cylindrical vessel at first has water up to 1 meter. And then we add those iron pellets, and as you know from experience, the water, the free surface is going to go up and up and up because there's more and more volume that's being displaced. And at some point, the iron pellets are going to reach the free surface of the water, and we have to find what is the height at that point. And we know a couple of things, such as densities, and we know this initial height as well. And we also know that the vessel is cylindrical. This is important, but not as important as you might think. But yeah, that's the question. So here's the first thing I would write. So this average density here is might confuse some people. So this 4,070 kilograms per meters cubed, what exactly is the average density of the contents? Now, before I tell you what this is, I'll tell you what this is not. So the average density is not the density of the iron plus the density of the water divided by 2, right? Because, well, on one hand, if you take 7,140 plus 1,000 and if you divide that by 2, you are not going to get this, okay? That's on one hand. On the other hand, the definition of average density is something very different. So average density is simply put the total mass of whatever's in the vessel, so that's the water and the pellets, divided by the total volume. So that's the volume of the water plus the volume of the pellets. So it's a simple formula, but don't do it this way. So the average density is not the average of the two densities, okay? Keep this distinction in mind. So the total mass, right, is of course the mass of the iron plus the mass of the water. So I'm using O for water simply because they're using O for water as well, and I for the pellets or for iron. And then for the total volume, of course, that's the volume of the iron plus the volume of the water. Okay? So that's what we'll use, but then we'll try to look at each individual term and see what we can how we can write it and how we can just find h from this expression. So let's look at this first. Let's take them in order. So the first term is the mass of the iron. So this is the mass of the pellets basically. So it's the density of the iron multiplied by the volume of the iron. Now, the volume of the pellets, or the total volume of the iron in the tank, is essentially the volume of one pellet multiplied by the total number of pellets, right? And this is quite tricky to do because we don't know how big the pellets are. And there's also, if you look here, you can expect to see some space in between the pellets. So finding this directly is not a very good idea, and in this problem you'll just reach a dead end. So we'll deal with this, but in a different way. But we'll come back to it. So let's now look at this. This is the mass of the water. So the mass of the water is essentially the mass of um, the stuff that's in between the pellets, right? Because the water fills every nook and cranny. And it just fills, so where there are no pellets, that's where you find the water. Which again, if you look at this scenario, it's difficult to calculate. Instead, consider what happens here. So however much water you have at first, that's how much water you have after the pellets have been added, right? The total mass of the water doesn't actually change. The shape of it changes, but the actual volume of it, and especially the mass of it, they don't change. So the mass of the water can actually be found from here. So it's the density of the water times the volume. Okay, so we know the density, and the volume is the volume of this sort of like cylinder, which is this big. So the volume of that cylinder is pi r squared. That's the cross-sectional area times h naught, right? So this is it. And that's how we write down the mass of the water, which again doesn't change after you add the pellets. So let's look at what's in the denominator. So in the denominator we have the volume of the iron, which again is tricky to get your head around, or not to get your head around, but it's tricky to calculate because we don't know anything about the pellets. What we do know is that the total volume, let's write that here. The total volume is made up of the volume of the pellets plus the volume of the water, right? Which means that I can write the volume of the iron as the total volume minus the volume of the water. So the volume of the water we know, right? We found it here. So it's pi r squared times h naught. So let's write as Vt minus pi r squared h naught. Now, what is the total volume? Well, the total volume is the volume of the pellets plus the water, which is essentially the volume of this cylinder here, which again, it's just the volume of a cylinder. So that's pi r squared times the height. The height in the final case is h, so which we don't know, and minus pi r squared h0, which is pi r squared times h minus h0. So we have actually found an expression for the volume of the pellets, not by considering the individual pellets because we don't know anything about them, but by considering the total volume and the volume of the water. So we subtracted one from the other and we found a, a reasonably good expression for the volume of the iron. Right. So well, we have this one as well, but this one we just saw it's pi r squared times h naught. So let's put everything together and let's see what we get. So the average density equals the mass of the iron. Now remember, the mass of the iron was the density of the iron times the volume of the iron. So we have the density of the iron. The volume of the iron we just got in that indirect fashion here. So that's times pi r squared multiplied by h minus h naught. And then we have plus this, that's the mass of the water. So that's plus rho 0 pi r squared times h naught. And then in the denominator, we have the same things that we have on top, except there's no density. So we just have this and this. So that's the volume of the iron, pi r squared, h minus h naught, and then plus rho 0 pi, sorry, there's no rho 0 here, there's pi r squared h naught. And you'll probably be able to tell that you can actually simplify what's on the bottom. So this cancels with this, and it's the total volume we're looking at. So the bottom is just going to be pi r squared h, right? So Vi plus Vo is Vt, according to this. Vt is equal to this, and that's what I wrote here, okay? Now, thankfully, pi r squared cancels out from everywhere, which is good because we don't know what the radius of the cylinder is, and it turns out it's not part of the problem. So the average density equals the iron density times I h minus h naught plus rho 0 h naught, and this is divided by h. And right now, we have this expression, which is just one equation with one unknown. So the only thing we don't know from here is h, which appears here, and it appears here as well. So the only thing left to do is to rearrange things to find h. So let's do that. If I cross multiply, I have rho dash times h equals rho I h. I'm just going to expand the bracket, minus rho I h naught plus rho naught h naught. So let's collect all the h terms. So we have this term with h and this term with h. So let's maybe bring this one here, and we'll bring those two terms on the left hand side of the equal sign, and that's what we'll have. So rho I times h minus this, so minus rho dash times h equals, and now when we move those to the other side, we have rho I h naught minus rho naught h naught. So let's factorize a couple of things. We have h times rho I minus rho dash. This is going to be equal to h naught times rho I minus rho naught. So h is going to be equal to h naught times rho I minus rho naught over rho I minus rho dash. And this is a very nice final expression. We haven't used any numbers yet, and as you've probably noticed, I don't really like using numbers. The main reason is that when you get to this form, you know immediately that the answer, you don't know if the value of the answer is going to be correct, but you know it's going to have the right units because you expect something in meters at the end, right? Because you're looking for a height. And look what happens on the right hand side. This is in meters because it's h0, it's the 1 meter, it's the initial height. Now, this is a density. Well, this is a density divided by another density, which won't actually have any units. So that fraction is non-dimensional, so no units. So the units on one side are going to correspond to the units on the other side. So from this perspective, everything is fine, right? If you had something like, if your final answer looked something like this, so maybe it was rho I times rho 0 divided by rho I minus rho dash, for example. If you go to this part, then you would know that the answer is not correct simply because the units don't hold, right? This is meter. This fraction is going to be measured in kilograms per meters cubed. So if you multiply meters by kilograms per meters cubed, you're not going to get meters back. Okay, you're going to be stuck with kilograms. But here, at least you know that you've passed this sort of sanity check and then your units are consistent. So the only thing left to do is put some numbers in. So H naught is 1 meter. Rho I. Now, rho I is the density of the iron, which is 7,140 minus 1,000, that's the water density, and that's over 7,140 minus 4070. Right. So we just have to find out what this fraction is. So the top is going to be 6,140, and let's see, on the bottom I have 3,070. So the final answer is whatever this fraction is, which is going to be 2. It's a very nice round number. So let's quickly recap. We have a cylindrical vessel with an initial height of water. So we have water being filled up to 1 meter height, and then we add some iron pellets. We don't care what size they are, but what we care about is that at the end, when we finish adding all the pellets, the free surface is just covering the topmost layer of the pellets. And then using this idea of average density, not the average of the two densities, but the average density, we're able to find the height by doing a bit of wizardry. So essentially, we don't know anything about the palette, so we don't know anything directly about the volume of the total iron pellets, but we found that by subtracting from the total volume by doing a bit of geometry using volumes and whatnot. So by doing that, we have just well, we've done some manipulations, and we have this expression where we know everything. It's dimensionally it works as well, so the units on both sides are the same, and the final answer turned out to be 2 meters. So the final height here is 2 meters, and that's the end of the question.